Good morning. In today's session, we are supposed to study about the types of equalization. So, in previous session, we have seen about the intersymbol interference. It is the form of distortion of a signal in which one symbol interferes with the adjacent, or we can say a subsequent symbol. It means what? We can say that will be an unwanted phenomenon in which we are having the interference. So we can say here previous symbol has similar effect as a noise, and thus it will make that communication less reliable. The spreading of a pulse beyond its allotted time interval will causes to interfere with neighboring pulses. Then we have seen about the equalization. So there are different types of equalizations like zero forcing equalizer, least mean square error equalizer, automatic and the adaptive equalization. So when we are saying when a signal is transmitted through a channel, it will undergo changes in the amplitude and phase. That will depend on a channel characteristics. But if we are saying that channel frequency response is not ideal, at that time, different frequency component will undergo different attenuation at a different delay. So the frequency response of such channel is such that its amplitude response is not constant and phase response is not linear. In that way, we are saying there is no equalization. So in order to combat the effect of non-ideal frequency response, we can use a filter at the front end of receiver, which has characteristics that will be exactly opposite to that of the channel filter. So we can say this can be done by using the equalizer, which will equalizes the effect of channel filter. So we can say that filter as a equalizer because that filter is operating in exactly opposite to that of a channel filter. So here we are saying we are supposed to study about the different types of equalizer like zero forcing equalizer, minimum mean square error equalizer, least mean square error equalizer, automatic and adaptive equalizer. We can say as a decision feedback equalizer. So zero forcing already we have seen. What we are saying here, it eliminates or minimizes the interference with the neighboring pulses at their respective sampling instant only. And we can done this by transversal filter equalizer, which forces the equalizer output pulses to have zero values at the decision making or the sampling instant. So here when we are saying, when we are having the value of tap gain that will be equal to 1 and clock equal to 0. So here when output of filter will be same but it will be only delayed at that time, we can adjust the tap gains. We generate additional shifted pulse of proper amplitudes that will force the resulting output pulse to have desired value. So we can say the output is the sum of that pulses. So here we are saying we can use the zero forcing equalizer, which will work exactly opposite to that of a channel filter. So here the tap gain can obtain by solving the set of equations. We can solve these equations in like linear equations, or you can put these equations in the form of matrix. So now we are supposed to study about the least mean square error equalizer. So another approach to equalization is the least mean square error equalizer. Does not try to force the pulse sample to 0, because when we are saying about the zero forcing, it is forcing that pulses to become 0. But here it will not try to force the pulses sample to 0 at 2n points. Instead that the mean of squared error over a set of output sample we can minimize, and this method will also involves simultaneous equations. It means what? It can solve equations simultaneously. Now we can see the another method which also we can use as a equalizer. So we can see automatic and the adaptive equalization, in which the setting of tap gains of equalizer cannot be done automatically. Can be done automatically. As a name given here, automatic and the adaptive equalization. It means what? Here we are supposed to set the tap gains value. So here we can set that values automatically by using a special sequence of pulses prior to a data transmission. And here we can use interactive technique to obtain the optimum tap gains. So in adaptive equalizer, the tap gains are adjusted continuously during the transmission. Here we have finished about the different types of automatic equalizer. There will be question like explain equalizer and its different types. So you are supposed to explain these types in the short manner. Now we are supposed to study about the new topic, that is nothing the I pattern. So when we have seen about the intersymbol interference, we are saying it will give us the distortion of a signal, where symbol will interfere with its adjacent symbol, and that will be the unwanted phenomenon. So here one way to study the intersymbol interference in a data transmission system experimentally is to apply receive wave to a vertical deflection plates of oscilloscope and a sawtooth wave at a transmitted symbol rate to horizontal deflection. It means what? Here, when successive symbol intervals are translated into a one interval on a oscilloscope display, that effect of channel filtering and the channel noise can be seen by observing the pattern. A resulting display we can say as a eye pattern because of we can see that with a human eye. It means what? Here eye pattern symbol, eye pattern will shows the combined effect of all interference impairments on a overall system performance. So here if we are supposed to study about the intersymbol interference in a digital transmission system at that time, we can apply receive wave to a vertical deflection plate of an oscilloscope and a sawtooth wave at a transmitted symbol to horizontal deflection plate when we are watching the waveform on oscilloscope at that time. So here we are saying the successive symbol intervals are translated into a one interval on an oscilloscope because that effect of channel filtering and channel noise we can see by our naked eyes. So we can say that resulting display as a eye pattern. So we can say about the eye pattern, it will be defined as the synchronized superposition of all possible realization of the signal of our interest. That will be the received signal, we can say as a received output, which can be viewed within a particular signaling interval. And we can say eye pattern will provide a great deal of useful information about the performance of data transmission system. So here you can observe the waveform. When the diagram A, you can say that is as a ideal channel filtering. If you see the diagram B, you can say that as a filtering with intersymbol interference. If you see the diagram C, we can say that as a there is an intersymbol interference but with noise. So here, when we are studying about the eye pattern at that time, we are saying we can see that display by our eyes, where we can see the effect of channel filtering and channel noise. So you can observe the diagram here. We are taking on the we are taking on the vertical y-axis. Here, if you see, we are watching here receive wave on a vertical deflection of a oscilloscope and sawtooth wave we can see that to a horizontal plane. So here if you see, we will get the base sampling time at the center. We can see that as a time interval over which we will get the received signal can be sampled. So here we are taking on the x-axis the time, and if you see, at the center we are saying here margin over noise, and we will get their base sampling time. So we can say distortion at a sampling time, and when we will get the interference we can say distortion of a zero crossing. So here the width of eye opening defines the time interval. If you observe this waveform, we can say here the width of eye pattern opening defines the time interval over which received signal can be sampled without error from the intersymbol interference. And the sensitivity of the system to timing error is determined by the rate of closure of our eyes, as the sampling time is varied here. And if you see its height, we can say the height of eye opening at specified sampling time. It will define the, you can see here we are giving the margin over noise. So we can say the height of eye opening at a specified sampling rate, it will define the noise margin of the system. And in the case of M-Array system, the eye pattern will contain the M minus I opening stacked up vertically one on other, where M is transmitted signal. So we can say here I pattern will give the information like the width of I, that will define the time interval. You can see here on the x-axis we are taking the time interval. So width of eye opening will define the time interval over which received wave can be sampled without error from a intersymbol interference. And the sensitivity of the system to the timing error is determined by the rate of chosen of eye. We can say as a slope of open eye. So it will be evaluated near the zero crossing point. And height of eye opening at specified sampling rate, it will define the noise margin. So we can say here maximum distortion is given by vertical width. You can see here we will get the maximum distortion that can be given by a vertical width of a upper or the lower portion of the eye at a sampling rate. And the range of amplitude difference is a measure of distortion which will cause due to a intersymbol interference. So the range of timing differences of a zero crossing is a measure of timing jitter. And the measure of noise merging we can take as a, you can see here we are taking the here noise margin. So we can denote that as a capital N suffix capital N. That will be the noise margin. And sensitivity of time error you can take as a capital ST. So here we have finished our intersymbol interference. Remaining we will see in the next class. Thank you.